Welcome to Educator.com. We're going to continue our lessons on polynomials by discussing roots and zeros. Okay, the number of roots can be determined by looking at the degree of the polynomial equation, because a polynomial equation of degree n has n roots. So this tells you only the number of roots. It doesn't tell you about the nature of the roots. The roots may be real or complex. For example, if I'm given a polynomial such as 5x to the 6 plus 2x cubed minus x squared plus 9x minus 2 equals 0, so a polynomial equation, I see that the degree equals 6. This tells me that there are 6 roots. 6 roots for this equation. Now, they can be real, and they could be, for example, these roots could be something like 1, -2. Those are rational numbers. They actually could be irrational numbers like the square root of 3. You also can have complex numbers as roots. Recall that complex numbers have 2 parts. So something like 2 plus 3i. And the first part here is real, and the second part is imaginary. And these are in the form a plus bi. We're going to talk in a few minutes about how these complex roots occur as conjugate pairs. For example, 2 plus 3i and 2 minus 3i would be a conjugate pair. Same values here, but opposite signs. Or 4 plus I, 4 minus I. So I know here I have 6 roots, but I have no idea if they're real, rational, irrational, or complex, or what combination of those. However, I can determine at least some of that through using Descartes' rule of signs. And there are 2 sections to this rule. The first section helps you determine the possible numbers of positive real roots. Then we'll talk about determining the possible number of negative real roots. So first, just looking at the positive real roots. Okay, so if we let p of x be a polynomial with real coefficients. So no imaginary coefficients, just real coefficients, arranging in descending powers. So recall that descending powers would be something like f of x equals x to the 6th plus 5x to the 5th plus 7x to the 4th minus x cubed plus 6x squared minus 2x plus 4. So this is a degree 6 polynomial, and I have 6, 5, 4, and on down. If you are trying to work with Descartes' rule of sign, the first thing to do is check the polynomial, and if it's not arranged in descending powers, you need to put it that way. Okay, so I've got this arranged in descending powers. The number of positive real roots is the number of changes in sign of the coefficients, or is less than this by an even number. Let's look at what that means. I want to look for the number of sign changes of the coefficients. So here I have, this is a 1, this coefficient, and that's positive. 5 is positive. 7, positive. -1. So there's a sign change. This is positive. This is negative. So that is 1 sign change. Okay, now here I'm going from -1 to +6. Again, I have a sign change. Here I'm going from a positive to a negative. Another sign change. Negative to positive. Another sign change. That gives me 1, 2, 3, 4. 4 sign changes. Means there are 4 positive real roots, or less than this by an even number. So less than 4 by an even number. So that would mean 4 minus 2 would give me 2. Or another even number 4. 4 minus 4 would give me 0. 4, 2, or 0 positive real roots. So again, take the polynomial, arrange it in descending powers, and then look at the number of sign changes. I have 1, 2, 3, 4 sign changes. That tells me that I will have at most 4 positive real roots. However, I may have less than this by an even number. So 4 minus 2, 2. 4 minus 4, 0. So I have 3 possibilities. I may have 4 positive real roots, 2 positive real roots, 0 real roots. And I have, since the degree equals 6, I have a total of 6 roots. I have a total of 6 of these. 4, 2, or 0 may be positive real roots. Okay. The second part of this is looking at the number of negative real roots. The number of negative real roots is the number of changes in sign of the coefficients of the terms p of negative x, or is less than this by an even number. Let's continue on with the example that we just looked at, where we were given f of x equals x to the 6th plus 5x to the 5th plus 7x to the 4th minus x cubed plus 6x squared minus 2x plus 4. Now, I found there were 4 sign changes, which means 4, 2, or 0 positive real roots. For the negative real roots, I have to look at f of negative x. So I need to change these x's to negative x. And be very careful with the signs. Okay, so this is going to give me a coefficient here of negative 1. But if I take a negative to an even power, it's going to become positive. Negative 1 to the 6th power, it's going to become positive. So this is going to give me f of negative x. Here is just going to be x to the 6th. Here I have negative 1 times x. You can look at it that way. It's negative 1 times x to the 5th. Well, if I take a negative 1 to an odd power, it's going to remain negative. So this is negative x to the 5th times 5. So this is going to give me negative 5x to the 5th. Here I have a negative coefficient to an even power. It's going to become positive. So this is really 7x to the 4th. Here I have a negative coefficient to an odd power. So it will remain negative. So this is negative x cubed, but it's times a negative. So negative x cubed times negative 1. This becomes plus x cubed. Okay, I have a negative x. This is actually, should be outside. Negative x squared is going to give me negative x times negative x. That's going to give me a positive. So this is going to be plus 6x squared. Here I have negative x times negative 2. That's plus 2x. And my constant remains positive. Okay, number of sign changes. So I want to look for the changes in sign. This is positive. This is positive out here. So positive to a negative, that's 1. Negative to a positive, that's 2. This stays positive, 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 positive. Number of sign changes equals 2. Okay, so the number of negative real roots is the number of changes in sign of the coefficients of the terms p to the negative x, or less than this by an even number. Therefore, I'm going to have 2 negative real roots, or less than this by an even number. Well, 2 minus 2 is 0. Can't go any lower than that for the number of roots. So 2 or 0 negative real roots. Again, this power is 6. I have 6 total roots. I have 2 or 0 negative real roots. And last slide, we talked about having 4, 2, or 0 positive real roots. So we covered the real roots. There also may be complex roots. So let's talk now about the total roots and the different combinations that you could have. So we can use Descartes' rule of signs to determine the possible combinations of the real and complex roots. So in that example above, f of x equals x to the 6th plus 5x to the 5th plus 7x to the 4th minus x to the 3rd plus 6x squared minus 2x plus 4. Total roots, this is real and complex, equals 6. Positive real roots, using Descartes' rule of sign, I found that I could have 4, 2, or 0. Negative real roots, I found f of negative x and looked for the sign changes and found 2 of those. So the number of negative real roots is, so the number of real roots, negative real roots, could be 2 or 0. Now I can figure out the combinations. I know that they need to total 6, and I have my positive real roots, possibilities, and my negative real roots. And the last part of this is complex roots. So I have positive real roots, the number of negative, and the number of complex. And these need to total 6. Must equal, the total must equal 6. So I said for positive real roots, I could have 4. Then I may have 2 negative real roots. 4 and 2 is 6, so that leaves me with no complex. I could have 4 positive real roots. I could have 0 negative real roots. 4 and 0 is 4. To total 6, I'll have to have 2 complex roots. Okay, another possibility. I have 2 positive real roots and 2 negative real roots. 2 and 2 is 4. 2 more complex roots will give me 6. Or I could have 2 positive real roots and 0 negative real roots. 2 and 0 is 2. To total 6, I'll have 4 complex roots. Okay, finally, I may have 0 positive real roots, 2 negative real roots. 0 and 2 is 2, so I'd have to have 4 complex roots. Okay, then I may have 0 positive real roots and 0 negative real roots. That gives me 0 and 0. So to total 6, I would have to have 6 right here. And since 3 times 2 is 6, I expect 6 combinations, and that's what I have here. So Descartes' rule of signs and knowing that the degree is 6, so I have 6 total roots, allows me to figure out the possible combinations of the roots of a polynomial. Conjugate roots. Okay, we talked a bit about complex conjugates and the fact that there are complex roots, but getting into a bit more detail. If the polynomial p of x has real coefficients, so the coefficients are not imaginary numbers, which is what we'll be working with is real coefficients for now. The complex roots of p of x occur as complex conjugates. And you saw this earlier on when we worked with quadratic equations and quadratic functions. Thinking about something like this. X squared plus 4 equals 0. If I wanted to find the solutions for this, I could say, okay, x squared equals negative 4. Now, using the square root property, I take the square root of both sides, and this gives me x equals plus or minus the square root of negative 4. Recalling that the square root of negative 1 equals I, then I can rewrite this as x equals plus or minus the square root of negative 1 times the square root of 4, or x equals plus or minus I times the square root of 4, or x equals plus or minus 2I. And we can look at this also in a different way. We can say x equals 0 plus 2I, or x equals 0 minus 2i. And you can then see that this is a pair of complex conjugates. And it's because of this, where we're finding the square root, that we end up with plus or minus some number. And therefore, these polynomials occur, the complex roots of polynomials occur as complex conjugates. Another example of complex conjugates would be, say, 8 plus 5i and 8 minus 5i. So same values, but switch the signs. Or 2 plus 7i and 2 minus 7i. And this explains why, when we talked about the number of real roots, negative real roots, positive real roots, we said it was that number, say 4, or less than that by 2. And the reason it goes down by pairs is because the complex conjugates occur in pairs. So they could take up 2 of the spots for the roots, and so they're going to decrease the number of the real roots by 2 or multiples of 2. Okay, here we're asked to solve this equation, polynomial equation, x cubed minus x squared minus 6x equals 0. I'm going to solve this by factoring, and the first step is to factor out the greatest common factor. And here I see I have a common factor of x. There's an x in each of these. So factor that out. This is going to give me x times x squared minus x minus 6 equals 0. Don't forget to bring this x along as you factor this, because this is going to give us one of the solutions. So I have x squared minus x minus 6 that I need to factor. This is in the form x plus something, a constant, x minus a constant, because this sign is negative. Factors of 6. 1 and 6, 2 and 3. And I need these to add up to negative 1. And their signs are going to be opposite. So these are close together. 2 and 3 are close together. So if I make the larger one negative and the smaller one positive, I'm going to get a negative 1. Therefore, 3 is negative and 2 is positive. Now, according to the zero product property, if any of these terms, x plus 2, or x minus 3 is 0, then this product will be 0, and it will equal the right side of the equation. Therefore, x equals 0, and make sure you don't leave this one out or you'll be missing one of the solutions. X plus 2 equals 0, or x minus 3 equals 0. So here, I don't have to do anything further with this. I just have that one of the solutions here is x equals 0. Here, I have to subtract 2 from both sides to get x equals negative 2. And here, I need to add 3 to both sides. So, solutions. X equals 0, x equals negative 2, and x equals 3. These are all solutions to this equation. And I solved this by factoring out the greatest common factor, x, factoring this trinomial, and then using the zero product property to solve for x in each of these expressions, terms. Okay. Here I'm asked to solve x to the 4th minus 256 equals 0. This is actually the difference of two squares. This is in the form a squared minus b squared. So it's going to factor out to a plus b, a minus b. And if you look at it and think about it this way, x squared squared is x to the 4th. And if you look at this one, 256, and take the square root of that, it's actually 16. So if you look at 256 and take the square root. Therefore, this is telling me that a equals x squared and b equals 16. So I can factor it as follows. A plus b, so that's x squared plus 16 times a minus b, or x squared, minus 16. Okay, I'm looking at what I have. I can't do anything else with x squared plus 16. But I recognize, again, here I have the difference of two squares. This time, a equals x and b equals 4. So it's going to factor out to x plus 4 x minus 4. And these are set equal to 0. Now I use the zero product property, which is going to tell me that I could have x squared plus 16 equals 0, x plus 4 equals 0, x minus 4 equals 0. Now let's work at these simpler ones first. Simply subtracting 4 from both sides to give me x equals negative 4. Adding 4 to both sides, x equals 4. So I have two of my solutions. Now looking over here, a little bit more complex, subtract 16 from both sides. That gives me x squared equals negative 16. Now I'm going to take the square root of both sides. And you can see that this ends up being plus or minus the square root of negative 16. And this is a negative number. And since I know that negative 1 equals I can rewrite this as x equals plus or minus I times the square root of 16. Well, the square root of 16 is 4. So this gives me complex conjugate pair plus or minus 4i. So I have 4 solutions. X equals 4i, x equals negative 4i, x equals 4, and x equals negative 4. And let's just think about Descartes' rule of signs and show that it predicted the possibilities for the type of roots that I could get. Since I have x to the fourth minus 256, if I look at the number of sign changes for this, this is positive to negative. So 1 sign change. This tells me that I'm going to have 1 positive real root, or less than that by an even number. But I can't go, because then I'd be going into negative numbers, and I can't say that there's negative 1 real roots. That wouldn't make sense. So it's just 1 positive real root. Now, looking at f of negative x, this gives me negative x to the fourth minus 256. Well, this negative 1, when you take it to the 4th power, is just going to become positive. So this gives me this. And again, I have 1 sign change. So this tells me that I have 1 negative real root. Since the degree here is 4, I have 4 total roots. So this is going to leave me with 1 positive real, 1 negative real, and 2 complex roots, which is exactly what I see. Positive real, negative real, and a set of complex conjugates. Determine the possible combination of positive real roots, negative real roots, and complex roots. So we'll use Descartes' rule of signs to determine this. And we'll start out by thinking about the total. Since the degree is 3, there are 3 total roots. Now, using the rule of signs, I'm going to look for f of x and the sign changes. This is 2x cubed minus 3x squared plus 4x minus 5. Number of sign changes. Well, this is positive and this is negative. That's 1. I'm going from negative here to positive here. That's 2. From positive to negative, that's 3. So number of sign changes equals 3. Therefore, number of positive real roots is 3, or less than this by an even number. So 3 minus 2 is 1. Can't go any lower than that. If I subtracted by 2 again, I would get a negative number. So I have either 3 or 1 positive real roots. All right, now let's look at the negative scenario for f of negative x to figure out the negative real roots. 2 times negative x cubed minus 3 times negative x squared plus 4 times negative x minus 5. Okay, this is going to give me f of negative x equals, this is going to remain negative, so this is going to give me negative 2x cubed. Negative and a negative squared is going to give me a positive, so this will become x squared. This is negative here though, so negative 3x squared. 4 times negative x, negative 4x minus 5. Okay, number of sign changes. None, none, none. The signs are all negative for the coefficients of f of x, negative x. So number of sign changes equals 0. So 0, negative, real roots. Okay, so let's figure out what we have going on here. We have positive real roots, negative real roots, and complex. And remember, these need to total 3. Positive real, I could have 3. Negative real, 0. I need them to total 3. This already does. So the complex is going to be 0. So this totals 3. Okay, another possibility is I have 1 positive real root, 0 negative real roots. 1 and 0 is 1. I need it to total 3, so there must be 2 complex real roots. So the possible combination of positive real roots, negative real roots, and complex roots is 3, 0, 0, or 1, 0, 2. And I know I have 3 total roots because the degree is 3. I used Descartes' rule of sign to tell me that I have either 3 or 1 positive real roots. I have 0 negative real roots. And then figuring out what's lacking to get my total of 3, I could fill them in with complex roots. Okay, determine the possible combinations of positive real roots, negative real roots, and complex roots. Degree equals 4, so I have 4 total roots. F of x equals negative 3x to the 4th minus 4x cubed plus 2x squared plus 6x plus 7. So positive real roots. Let's look for sign changes between these coefficients. Negative to a negative, okay, negative to a positive, so that's 1. Positive to a positive, no sign change. Positive to a positive again. So positive real roots equals 1. And I can't go by less than that because if I subtracted 2, I'd go into negative numbers. So the number of positive real roots is 1. Now, looking at negative real roots, I'm going to take f of negative x to get negative 3 times negative x to the 4th minus 4 times negative x to the 3rd plus 2 times negative x squared plus 6 times negative x plus 7. Okay, this gives me f of negative x equals, well, negative 1 to the 4th power, this will become positive. So I have negative 3 x to the 4th. Here, negative x cubed, this is going to remain negative as a coefficient, times negative 4, that's going to become positive. So this is going to give me plus 4x cubed. Negative x squared is going to give me positive x squared times 2. So that's plus 2x squared. 6 minus negative x, negative 6x plus 7. Okay, negative real roots is going to be determined by the sign changes of the coefficients of f of negative x, according to Descartes' rule of signs. Negative to a positive, that's 1 sign change. That stays positive. Positive to a negative, 2. Negative to a positive, 3. So here I have 3 or less than that by an even number. So 3 minus 2 is 1. Can't go any less than that. So I have a total of 4 roots. I have 1 real root and either 1 positive real root and either 3 or 1 negative real roots. So let's look at the possibilities. Positive real roots, negative real roots, complex. Okay, positive real, 1. Then I could have a negative real root totaling 3. 1 plus 3 is 4. I only have 4, so complex must be 0. Or I could have 1 positive real root and 1 negative real root. And I'm going to total those to get 2. But I should have 4. So in this case, there'd be 2 complex roots, a pair of complex conjugates. Okay, so I determined there were 4 total roots because the degree here is 4. Using Descartes' rule of sign, the positive case, f of x, I found that there is 1 positive real root. F of negative x gave me 3 sign changes, so there are either 3 or 1 negative real roots. And then to get a total of 4, I had 0 complex roots in this case and 2 in this case. Thanks for visiting educator.com, and I'll see you soon.